Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. In this lecture, we will see the description of BGW MPC protocol, where we will now consider that in the circuit we also have nonlinear gates which are also known as multiplication gates, and then we will see what are the challenges which we face when we try to securely evaluate the multiplication gates in the circuit. So, just to quickly recap, this is the BGW approach for shared circuit evaluation, where we assume that the function which needs to be securely computed is represented by a publicly known arithmetic circuit consisting of linear gates and nonlinear gates. And the shared circuit evaluation starts with secret sharing the respective inputs of the parties. This is done by the parties themselves. So, each party acts as a dealer and secret shares its input with the degree of sharing being t. And the important thing is that the instance of secret sharing is random, in the sense that if P1 is the dealer and if it wants to secret share the value x1, it will be generating random shares for this value x1 and distributing the shares and so on. And then once all the input values are secret shared, the parties, each party starts evaluating a copy of the circuit, but not on the clear value, but rather on the shares of the value. Okay. So, in a more detail, parties try to maintain what we call as the BGW gate invariant, where it will be ensured that if there is a gate input, if there is a gate whose inputs are secret shared randomly with the degree of sharing being t, then the gate output is made available to the parties in a secret shared fashion, where the degree of sharing is still t and the vector of shares is a random vector of shares. And in this whole process, neither the gate inputs will be revealed nor the gate output will be revealed. So, for instance, if I consider this input gate, what I am saying is that once the value x1 and the value x2 are secret shared, the parties will try to ensure that they have their shares of this intermediate I1, and then the parties will ensure that they have the shares of this intermediate value I2, and then they will ensure that given the shares of I1 and I2, the parties own their respective shares of I3, and then this C is a publicly known constant. So, the parties will ensure that given the shares of I3, they obtain their respective shares of Y, and finally, once all the values, intermediate values in the circuit have been made available in a secret shared fashion, the parties go and publicly reconstruct the final output value. Okay. And I stated earlier that to maintain this gate invariant, the parties may need to interact. We had seen that the n comma t secret sharing scheme, which is used in the BGW protocol, is the Samir secret sharing, and since Samir secret sharing satisfies the linearity property, to maintain the gate invariant for linear gates, it does not require any interaction among the parties. But we will see that when it comes to the multiplication gates, to maintain the gate invariant, the parties need to interact. Okay. So, the focus of this lecture will be that can we maintain this BGW gate invariant without asking the parties to interact even for the multiplication gates, and we will see that the answer is no. Okay. So, before going into that, here is a quick recap of the linearity property of n comma t secret sharing, where we had seen that any linear function of secret shared inputs can be computed by applying the function on the shares of the input values itself. So, for instance, if you want to compute S plus C, where C is publicly known, but S is not known, but rather secret shared, then by adding the shares of S with the value C, the parties obtain a secret sharing of S plus C. In the same way, if S and S prime are two unknown values, but secret shared with the same threshold T, then to obtain shares of S plus S prime, each party just has to go and add its respective share of S and S prime. Similarly, if S is unknown and if C is a publicly known value, and if every party multiplies their respective shares of S with this public known constant C, then they obtain their respective shares of C times S. But when it comes to multiplying two secret shared values S and S prime, we had seen that if we ask the parties to just locally multiply their respective shares of N as S prime, then the resultant vector of shares will constitute a secret sharing of S time S prime, but the degree of sharing will be 2t and not t, because the resultant vector of shares will now lie on a polynomial of the degree 2t and not of degree t, right. Namely, this polynomial 8z times bz will be a 2t degree polynomial, where az is the polynomial for secret sharing the value s and bz is the polynomial secret sharing the value s prime. Okay. So, now we will see that what are the challenges which we face when we try to maintain the BGW invariant for evaluating the multiplication gates. And to demonstrate the challenges, I will consider a very simple scenario. I will consider a 4-party function where party 1 has the input x1, party 2 has the input x2, party 3 has no input and party 4 has no input, and all the 4 parties are interested to learn the product of x1 and x2, where x1 and x2 are some field elements. And I will assume that out of these 4 parties, up to 2 parties can be passively corrupted by a computationally unbounded adversary. And the security goal is to ensure that the corrupt parties should not learn anything additional beyond what they can learn from the product of x1 and x2 and the inputs of 2 corrupt parties which are under the control of the adversary. Okay. So, this is a very simple function consisting of just one multiplication gates. There is no linear gate, there is just one multiplication gate and you obtain the function output. Okay. So, that is our goal. So, now let us see what goes wrong if we try to blindly follow the BGW MPC protocol for this circuit, where we start with asking the input holders to secret share their respective inputs, and then we multiply the shares of x1 and x2, and then we finally go and publicly reconstruct the vector of shares of x1 dot x2. We will see what exactly goes wrong in this protocol. So, we start with the inputs and we ask P1 to act as a dealer and P2 to act as a dealer and independently secret share their respective inputs x1 and x2 with a 2 degree polynomial, random 2 degree polynomial. Okay. So, here is the table of values. So, x1 will be secret shared and it will produce 4 shares. The first share will be with the first party, second share with the second party and so on. Similarly, P2 will act as a dealer and it will pick a 2 degree polynomial, a random 2 degree polynomial whose constant term is x2, generate 4 shares and distribute the individual shares to the respective parties. This will complete the input sharing phase. There are no more inputs for this function. And now parties start evaluating the circuit. So, they now have the inputs for this multiplication gate available in a secret shared fashion. So, they take the first gate in this circuit, which is the multiplication gate. So, let the parties locally multiply their respective shares of x1 and x2. So, party 1 multiplies x11 with x21. When I say multiply as per the field multiplication operation, and it will produce a field element, call it y1. Similarly, P2 goes and multiply multiplies its respective shares of x 1 and x 2, P 3 multiplies its respective shares of x 1 and x 2, and P 4 multiplies its respective shares of x 1 and x 2. And let this be the, let y 1, y 2, y 3, y 4 be the resultant vector of chairs, where the ith component is with the ith party. So, as we have seen earlier, this vector of values y 1, y 2, y 3, y 4, namely alpha 1 times y, alpha 1 comma y 1, alpha 2 comma y 2, alpha 3 comma y 3 and alpha 4 y 4, they constitute or they lie on a 2t degree polynomial. Okay. Because x 1 was shared through an a polynomial whose degree was t, b was secret shared through a t degree polynomial, call it as a b polynomial. The constant term was of a was x 1, the constant term of b polynomial was x 2, and now if you multiply these two polynomials you will get a c polynomial and its degree will be 2t. And the c polynomial evaluated at alpha 1, alpha 2, alpha 3, alpha 4 will be giving you y 1, y 2, y 3, y 4. So, that is why this vector of shares y 1, y 2, y 3, y 4, it constitutes an n comma 2t Samir sharing of y. And now, let as per the BGW protocol, since there are no more gates after this multiplication gates, they have, the parties have evaluated all the gates and the function output is available in a secret shared fashion. So, let the parties exchange the shares of y among themselves, that means y 1 is given to everyone, y 2 is given to everyone, y 3 is given to everyone and y 4 is given to everyone, and then they interpolate a 2t degree polynomial, namely the c polynomial, and get back the value y. Suppose this is the BGW protocol, right, which we use here to evaluate this circuit. Now, there are two problems with the above protocol, okay. And one problem is associated with the correctness property and the other problem is associated with the privacy property. So, let us see the problem associated with the correctness. Okay. So, consider a case where the number of parties n satisfies this condition, that means n is either equal to 2 times t or it is strictly less than 2 times t. Now, if this is the case, then the problem that we are going to face in the proposed protocol is that the value y need not be reconstructed back correctly, because this vector of shares y 1, y 2, y 3, y 4, they lie on a 2t degree polynomial. Okay. And to reconstruct a 2t degree polynomial through Lagrange interpolation, we need at least 2t plus 1 distinct values or 2t plus 1 distinct shares on that polynomial to uniquely reconstruct it back. But if we are in a setting where n is say less than equal to 2t, then even if all the shares of y are made public, we cannot reconstruct back the polynomial c of z correctly, and if polynomial c of z is not reconstructed correctly, you cannot reconstruct back y correctly, and hence the parties may not obtain the correct output. Okay. So, to make my point more clear, we are actually in this example in the setting where the number of parties is 4 and your t is equal to 2, right. And imagine that we take this specific example where x 1 is equal to 0 and p 1 shares x 1 equal to 0 through a 2 degree polynomial. So, this is a 2 degree polynomial, you can interpret it as z square plus 0 times z plus 0, and this polynomial will be evaluated at alpha 1, alpha 2, alpha 3, alpha 4, which I am taking to be 1, 2, 3 and 4 respectively. So, this will be your vector of shares for x 1, and say x 2 is equal to 1, it is secret shared through this polynomial. So, again this polynomial you can interpret it as z square plus 0 times z plus 1. So, this is a 2 degree polynomial. This polynomial evaluated at 1, 2, 3, 4 will produce this vector of shears. Now, let the parties multiply their respective shears of x 1 and x 2. Remember, all the computations are performed over Z 5, where the additions are addition modulo 5 and multiplications are multiplication modulo 5. So, this will be your y 1, y 2, y 3 and y 4. And now, if we interpolate the points y 1, y 2, y 3, y 4, of course, along with alpha 1, alpha 2, alpha 3 and alpha 4, we will be getting back this polynomial. I am not showing the computations in the slide, but you can verify it. If you interpolate the points 0 alpha 1 comma y 1, alpha 2 y 2, alpha 3 y 3 and alpha 4 y 4, you will be getting this polynomial. This polynomial is also a 2 degree polynomial, because I can interpret it as this. And now, if this is the polynomial which parties reconstruct back, then the output of the function which parties will obtain is 1. But that is not the correct output, because if x 1 is equal to 0 and if x 2 is equal to 1, then y should be 0. But what parties are reconstructing here? They are reconstructing 1 as the function output. And why this problem is happening? This problem is happening because the polynomial a polynomial was this z square plus 0, the b polynomial was z square plus 1. And now, if I consider this 4 values y 1, y 2, y 3, y 4, they lie on the c polynomial, and c polynomial has degree 4, because it is the product of a polynomial and b polynomial, each of which is of degree 2, and if you multiply 2 polynomials of degree 2, you will get a resultant polynomial whose degree is 4, and to reconstruct uniquely and correctly a 4 degree polynomial, you need 5 distinct points or 5 y values or y shares on that c polynomial. But we are having only 4 parties in the system. You do not have the 5th party who can provide you the 5th point on this c polynomial in the form of its share, and using which you can reconstruct back your y correctly, right. So, that is a correctness problem, and you can imagine that this problem is arising just for one single multiplication gate, but imagine a circuit where you have a computation of the form x 1 times x 2 times x 3 times x n, a computation of this form. So, you suppose you follow the same protocol there, where all the inputs are secret shared, and then say you locally you ask the parties to locally multiply their shares of x 1 and x 2, the degree of sharing becomes 2t. And now, you ask the parties to take this vector of shares and locally multiply their respective shares from this vector with the shares of x 3, then the resultant degree will become 3t, and like that the degree of the resultant output will keep on increasing after every multiplication, and finally, the degree may become so high that you do not have sufficient number of parties to provide those many shares during the reconstruction of that final output. So, that will lead to an error in the correctness property. So, that is the problem number 1 or challenge number 1. Okay. Now, let us see the second problem, second challenge associated with evaluating the multiplication gates, and this is related to the privacy property, and this is very subtle to understand. Okay. So, imagine for the time being that you are in a setting where n is greater than equal to 2t plus 1. That means, I take say for instance the same example, same setting where n is equal to 4, but now I am working in a setting where t is equal to 1. It is given to me that up to one party can be semi honestly corrupted, passively corrupted by an unbounded adversary. That means, we now no longer face that issue of correctness or problem 1 which we had encountered just now. Why so? Because now we have just one multiplication gate. If x 1 is secret shared through a degree t a polynomial, and if b is also secret shared through a random degree t polynomial, then my C polynomial will be of degree 2t, and I am assuming that I am in a setting where n is greater than equal to 2t plus 1. That means, if parties make public their respective shares of y, we have now sufficient number of shares to uniquely get back this C polynomial and take its constant term as the final output. So, correctness is no longer an issue, because I am ensuring that we are in the setting where n is greater than equal to 2t plus 1. But now the problem is that the resultant shares of y, which are obtained by locally multiplying the shares of x, they do not even though the degree of sharing is 2t, the resultant vector of y shares do not constitute a random vector of shares for the value y lying on a 2t degree polynomial. What does that mean? I mean here that if you take this C z polynomial and alpha 1 y 1, alpha 2 y 2, alpha 3 y 3 and alpha 4 y 4 lying on the C z polynomial, of course, the degree of C polynomial is 2t. I can no longer claim that C polynomial could be a random polynomial from the set of all possible polynomials of degree 2t whose constant term is y, right. So, remember this set P superscript y and 2t denotes the set of all possible 2t degree polynomial whose constant term is y. Okay. So, my claim is the C polynomial over which this values alpha 1 y 1, alpha 2 y 2, alpha 3 y 3 and alpha 4 y 4 lie is not a randomly chosen element from this set, or it is not a randomly chosen polynomial whose constant term is y and whose degree is 2t. What does it mean? When I say that I am picking a random polynomial whose constant term is y and whose degree is 2t, by that I mean that each of the coefficients of that polynomial except the constant term is randomly chosen. But the C polynomial that we are obtaining here is not a polynomial whose each of the coefficients except the constant coefficient or the constant term is randomly chosen from the field. Why so? This is because if we consider the C polynomial, it does not constitute an irreducible polynomial. What is an irreducible polynomial? So, we say a polynomial is reducible. Intuitively, informally we say a polynomial is reducible if it can be factorized into non-trivial polynomials. Okay. And what does non-trivial polynomials mean here? Basically, they mean polynomials whose degree is less than the polynomial which we want to factorize. So, in this case, that is a very high level definition of a reducible polynomial. So, in this case, the C polynomial can be indeed factorized into two factors, namely A polynomial and B polynomial, and the degree of both the A polynomial as well as B polynomial is strictly less than the degree of the C polynomial, because the degree of the C polynomial is 2t and the degree of the A polynomial is t and the degree of the P polynomial is t. So, that means even though that means that this C polynomial definitely is not a randomly chosen polynomial from this set, because if it would have been a randomly chosen polynomial, then with equal probability it could be a reducible polynomial of degree 2t whose constant term would have been y, or with equal probability it could have been an irreducible polynomial whose constant term would have been y and degree being 2t. But we know in this case that if parties just locally multiplies their respective shares of x 1 and x 2 and then publicly reconstruct the C polynomial, we know for sure that definitely this C polynomial is not one of any one of the polynomials randomly chosen from this set P of y comma 2t, because we know definitely for sure that it is definitely an it is definitely a reducible polynomial, because the A polynomial and the B polynomial constitutes the factors of this C polynomial. That means, this C polynomial is no longer a random polynomial, and this itself could be a privacy breach, because learning this C polynomial might end up leaking something about x 1 and x 2. And the problem that is happening here is, it is not only that the degree of sharing has increased, it has become 2t. The BGW invariant says that if the inputs, recall, if the invariant was, if the inputs are shared through a random polynomial, then output should be shared through a random polynomial. That is the invariant, and only when this invariant is maintained we can argue the security, because then we can argue that for each intermediate value adversary just sees t random shares lying on a random polynomial whose constant term would have been that intermediate value. But t random shares could be random shares on any polynomial, hence the adversary cannot infer anything. And remember, for the linear gates, if a polynomial is a randomly chosen polynomial whose degree is t, that means for the case of linear gate, if AZ is the member of a set of polynomials, it is a random member of the set of all polynomials of degree t whose constant term is x 1, B is a polynomial, it is a random member of the set of all possible polynomials of degree t whose constant term is x 2, and then if parties just locally add their respective shares of A and B, the resultant C polynomial, namely the AZ plus BZ polynomial, it also constitutes a random member of the set of all possible polynomials of degree t whose constant term is x 1 plus x 2, because if the coefficients of A are randomly chosen, of course except the constant term, and if same is the case for the B polynomial, then if you take component wise the coefficients and add them, that will give you the coefficient of z power I for this sum polynomial, and if the coefficients of z power I in the A polynomial and the B polynomial were random, you add two random coefficients, that will give you a random coefficient for z power I in the C polynomial. So, that is why this sum polynomial is still a random member of this set of all possible polynomials of degree t whose constant term would have been x 1 plus x 2. But that is not happening for the case of multiplication. Even though if A and B polynomials respectively are random members from the respective set of polynomials, I can't say that this C polynomial is a random member from the set of all possible polynomials of degree 2t whose constant term is x 1 times x 2. I can't make this claim, and that will lead to a security breach, privacy breach. So, let me demonstrate that concretely. Okay. So, again I take the setting where n is equal to 4, all computations performed over this field, and say x 1 is 1 shared through a 1 degree polynomial. This is the A polynomial, and these are the vector of shares for x 1, and the value x 2 is 4 shared through this polynomial, and this is the vector of shares for x 2. And I consider a scenario where P 3 is corrupt. Okay. So, that is why all the values in this table which are in bold are the values which will be seen by the corrupt P3 and which it will try to now analyze to learn anything additional about x1 and x2. So, P3 is the corrupt party. So, this will be the view of corrupt P3. It will see the share of x1, it will see the share of x2 and it will see all the shares of y because they will be made public and she will be seeing the C polynomial. Okay. So, correctness is not an issue here because the degree of C polynomial will be 2. Okay. So, you might be wondering that it is degree 1 here. No, in general it could be degree 2 because A polynomial could have degree 1, B polynomial could have degree 1. If you multiply, you might have a term of the term of the form z square in the C polynomial, but in this case the coefficient of z square is turning out to be 0, but overall C polynomial could be of degree 2 and we have sufficient number of parties to reconstruct back this C polynomial. So, the correctness is not an issue in this particular example. Now, what the corrupt P3 might do once the protocol is over, she is learning the final outcome to be 4. So, from her viewpoint, this could be one possible scenario with which the protocol has been executed. That means, she might be analyzing in her mind that it could be the case that input x1 was 1 and input x2 was 4 and the values that I have seen actually corresponds to that case. Or from her viewpoint, it could be the case that x2 is x1 equal to 2 and x2 equal to 2, or this could be the input scenario or this could be the input scenario. If at all this protocol would have been satisfying the privacy property, then adversary or the corrupt P3 could not pinpoint whether she has seen the execution with respect to this input scenario or this input scenario or this input scenario or this input scenario. And remember, for the case of linear functions, we have rigorously proved that indeed adding the shares of input values and then publicly reconstruct the function output does not reveal anything additional about the inputs of the parties other than what can be inferred from the function output. But in this particular case where the function is the multiplication of inputs, we will see that that is not the case. So, the question marks in the table are the unknown value from the viewpoint of the corrupt P3. So, now imagine the corrupt P3 makes an hypothesis that can it be possible that x1 was 2. As soon as she fixes x1 equal to 2, and remember the unknown A polynomial was a 1 degree polynomial. So, now as soon as she fixes x1 equal to 2, that means she is fixing the A polynomial passing through the points 0, 2, namely 0 and 2 will be a point on this unknown A polynomial, and she has seen the share 2 during the protocol. That means 3, 2 also is a point on that unknown A polynomial. And now, once 2 points are fixed, that automatically fixes the A polynomial. Okay. So, that fixes the A polynomial from the viewpoint of corrupt P3, and if this would have been the A polynomial, then the shares of P1, P2 and P4 would have taken these values. Now, once P3 has fixed x1 equal to 2 in her mind and the final result is 4, that automatically fixes x2 being 2. And now, if x2 is fixed to be 2, that means adversary or the corrupt P3 is now considering the case where the B polynomial should have passed through the points 0, 2 and 3, 4. Why 3, 4? Because her share for the unknown B polynomial that she has seen is actually 4. So, fixing x2 equal to 2 fixes the B polynomial to 2 plus 4z, and if the B polynomial would have been 2 plus 4z, then this unknown shares of P1, P2 and P4 for the x2 would have been this, and now it matches with whatever adversary or the corrupt P3 had actually seen during the protocol execution. Indeed, if x1 was 2 and secret shared through the polynomial 2 plus 0z, and if x2 was 2 and secret shared through the 1 degree polynomial 2 plus 4z, this will be the vector of shares for the respective parties, and after multiplying they would have obtained this y1, this y2. Indeed, they would constitute the corresponding y values, and they would have made these y values public, and hence it is quite possible that adversary, the corrupt P3, had actually seen an execution where x1 was 2 and x2 was 2. That is quite possible. So, this cannot be ruled out. Now, adversary takes the same set of values which she had seen in the protocol, right, namely her view. So, basically the values in the bold is the view of the corrupt P3, and we are trying to argue here that can I say that view 3 is consistent with all possible x1 x2 whose product is 4. So, we had shown that the view 3, so this is view 3, the values in bold here. Okay. So, this is view 3, and we had shown that it is consistent with x1 equal to 2 and x2 equal to 2. Okay. Of course, it is also consistent with x1 equal to 1 and x2 equal to 4, because that is precisely is the values with which the protocol has been executed. Now, the remaining two configurations are left from the viewpoint of the corrupt P3. Okay. So, let us consider the case where P3 is fixing x1 to be 4 and x2 to be 1, and she is asking in her mind, analyzing in her mind, can it be the case that my view has resulted because I have participated in an execution where x1 is 4 and x2 is 1. So, as soon as x1 is fixed to 4 and x2 is fixed to 1, then based on the argument that we had seen for the previous input configuration, it fixes the a polynomial to this value and b polynomial to this value. That means, if x1 would have been 4 and if P3's share would have been 2, then this would have been the full vector of x1 shares. In the same way, if x2 would have been 1 and if P3's share would have been 4, then this would have been the full vector of x2 shares. But this, if this would have been the case, then it can't be possible that P1 after multiplying its shares of x1 and x2 would have obtained y1 equal to 2. No, that is not possible, because his share of x1 would have been 0, his share of x2 would have been 2, and 0 into 2 should have given 0, and that means if this configuration or if this execution has been done, then P1 should have broadcasted 0 instead of 2 as its share. In the same way, P2 should have made public 3 as its share of y instead of 0, and P4 should have made public 0 as its share of y instead of 1, and this should not have been the C polynomial. C polynomial should have been the product of the polynomials 4 plus z and 1 plus z, which is not the case. That means, now corrupt P3 can say that definitely I have not seen an execution with respect to x1 equal to 4 and x2 equal to 1. So, that is ruled out from her viewpoint, and in the same way we can show here that she can rule out that view 3 is not consistent even with x1 equal to 3 and x2 equal to 3. That is not possible. That means, P3 can rule out that definitely these are not the pair of inputs of P1 and P2, and that is a violation of the privacy condition. And again I stress why this issue is happening. This issue is happening because this C polynomial is not a random polynomial from the set of all possible polynomials of degree 2t whose constant term is x1 times x2. Okay. And that is a problem here. Okay. So, with that I conclude this lecture, and to summarize, in this lecture we have seen that there are two challenges associated with evaluating the multiplication gates. The first challenge is associated related to correctness itself, namely if we just ask the parties to locally multiply their respective shares of the inputs of a multiplication gate, then the degree of sharing blows up and we will not have sufficient number of parties to reconstruct back that secret shared value. And the second problem is that even if we have sufficient number of parties to reconstruct back that secret shared output whose degree has become twice, that resultant vector of shares does not constitute a the resultant vector of shears does not lie on a random polynomial of degree 2t. Okay. For instance, it is not an irreducible polynomial, and that might itself be a issue of privacy. Thank you.